Welcome. Today we are diving headfirst into one of the most classic puzzles in all of genetics. Think of it like a genetic detective story. We've just been handed a case file. It's a jumble of data from a genetic experiment, and hidden somewhere inside these numbers is the precise order of 3 genes on a chromosome. Our mission, should we choose to accept it, is to sort through all the evidence, follow the clues, and crack this genetic code. So let's get our investigation started. So, here's our game plan for this investigation. First, we're going to lay out the mystery itself. Then, we'll learn how to sort the evidence, pulling out the most important clues. From there, it's time to interrogate our 3 main suspects, one by one. And once we've done that, we'll crack the code, revealing the truth, and finally draw the definitive genetic map that all of our evidence has been pointing to. You know, every great detective story kicks off with a bunch of clues that honestly don't make a whole lot of sense at first glance. And for us, that's exactly what we have. A list of offspring from a 3-point test cross. Right now, it just looks like a collection of numbers and letters. But trust me, by the end of this, we're going to see that it's actually a super detailed story about how genes are inherited. Okay, and here it is. This is our evidence. This table shows 8 different combinations of 3 genes. We'll just call them M, F, and W, and the number of offspring that were born with each specific combo. Now, the letters, they represent the mutant versions of the genes, the alleles, while those little plus signs, those are the normal or wild-type alleles. The answer to our big question is hiding in plain sight right here in these numbers. Our job is to find. So this is the whole point of our investigation. The central mystery is this: what is the correct order of these genes? We just don't know if the real order on the chromosome is MFW, or maybe FMW, or even FWM. Our entire investigation is focused on solving this one big mystery, because finding the gene that sits in the middle, well, that's the key that unlocks absolutely everything else. Right, so before we can even think about forming a hypothesis, we've got to bring some order to this chaos. I mean, any good detective will tell you that the most common and the least common pieces of evidence are often the most revealing. So that is exactly where we're going to start our analysis. First things first, we need to look for what's called the parental class. Think of these as the big players, okay? They are the most common outcomes you see in the data. And the reason they're so frequent is because they represent the original combination of genes from the parents' chromosomes, which were passed on directly without any of that genetic shuffling or recombination happening between them. So if we look back at our data, it's pretty easy to spot the 2 largest numbers, right? 253 and 231. These correspond to the genotypes +++ and MFW. Bingo. These are our parental genotypes. This tells us something huge. One parent contributed a chromosome with all the normal wild-type alleles, and the other parent gave a chromosome with all 3 mutant alleles. This is our baseline. All right, next we hunt for the complete opposite, the double crossover class, or DCOs. These guys are the rarest of the rare. Now, a crossover is just when chromosomes swap little bits of genetic material. For a double crossover to happen, 2 of these exchanges have to occur in the teeny tiny space between these 3 genes. It's kind of like lightning striking twice in the exact same spot. I mean, it's possible, but it is highly, highly improbable. And that very rarity is what makes them our single most valuable clue. Okay, let's scan our data again, but this time for the smallest numbers. And there they are, 47 and 31. The genotypes that go with them are M++ and +FW. This, my friends, is our smoking gun. These super rare offspring were created by that improbable double crossover event, and comparing them directly to our parental class, that's the secret to finding the middle gene. So let's just take a moment and rearrange our evidence based on what we just figured out. Look at that. It's so much clearer now, isn't it? We've got our 2 parental classes right at the top, our 2 double crossover classes, our smoking gun at the bottom, and then the 4 single crossovers are sandwiched in between. Our case file is finally organized. Now, the real detective work can begin. Okay, so we have 3 suspects for the identity of that middle gene. It could be F, it could be W, or it could be M. We're going to test each one with a really simple question. If you were in the middle, what would the double crossover offspring look like? Only the true middle gene is going to give us a prediction that actually matches our evidence. Let's bring in our first suspect, gene F. We're going to assume, just for a moment, that the correct gene order is MFW. Okay, let's predict the outcome. If the parental chromosomes are M-F-W and +++, a double crossover event always swaps only the middle gene. That's the rule. The genes on the ends, they stay put. So the F from the first chromosome would move to the second, and the wild-type plus from the middle of the second chromosome would move to the first. This would create offspring that are M plus W and plus F plus. That's our prediction. Now we compare. Our prediction was M plus W and plus F plus. But what was the actual evidence? Our rarest offspring, our smoking gun, are M plus plus and plus FW. This is a clear contradiction. The evidence does not support the hypothesis at all. Gene F is not in the middle. Case closed on that one. Suspect number 1 is cleared. All right, 1 suspect down, 2 to go. Let's move on to our next one, gene W. What if it's the one in the center? Let's put this hypothesis to the test. Let's run the simulation one more time. If the order is FWM, then our parental chromosomes have to be arranged that way too, FWM and plus plus plus. A double crossover swaps the middle gene, which this time we're saying is W. This would give us offspring with the genotypes F plus M and plus W plus. That's prediction number 2. And now we check it against the hard evidence. We predicted F plus M and plus W plus. The actual data says M plus plus and plus FW. Again, it's not even close. Our second hypothesis is definitively, totally incorrect. Gene W cannot be the one in the middle. Okay, this is exciting. We've ruled out F, and we've ruled out W. Now, by a simple process of elimination, we should have our culprit. But, a good detective always confirms the evidence. We absolutely need to test our final suspect to be 100% sure we've cracked this case. Our final suspect is gene M. Could the true order of genes on this chromosome be FMW? Let's put it to the test and find out. Okay, one last time, let's walk through it. We assume the parental chromosomes are arranged in the order F-M-W and plus plus plus. A double crossover event swaps only the middle gene, which in this case we're hypothesizing is M. So the first chromosome gives up its M and takes a plus, becoming F plus W. The second chromosome gives up its plus and takes the M, becoming plus M plus. This is our final and most crucial prediction. And now, the moment of truth. Let's compare. Our prediction is F plus W and plus M plus. The actual double crossover evidence from our data is plus FW and M plus plus. Now hold on a second. Remember, the order we write the genes in doesn't matter, just which ones are present. So F plus W is the exact same thing as plus FW, and plus M plus is the exact same thing as M plus plus. They are a perfect one-to-one match. We found it. We have confirmation. And there it is, clear as day. Gene M is the gene in the middle. We've officially cracked the code. The true sequence of these genes on the chromosome is FMW. The mystery is solved. Solving the gene order isn't really the end of the story. In a lot of ways, it's the beginning. Now that we finally know the correct sequence, we can go back to our evidence and organize it all properly, creating a true representation of the chromosome and all the crossover events that happened. Let's take a look at what that completed map looks like. And here it is, our final, correctly ordered table. The parental classes are FMW and plus plus plus. And look, notice how this single crossovers now make perfect sense. A crossover that happens just between F and M results in F plus plus and plus MW. A crossover just between M and W gives us FM plus and plus plus W. And of course, our confirmed double crossovers, F plus W and plus M plus, are right there where they belong at the bottom. Everything just clicks into its logical place. And that's really the key takeaway from all of this. What we've just done is so much more than just an academic exercise. By following the clues and using pure logic to figure out the gene order, we've actually started to read the chromosome's blueprint. We now understand its fundamental structure in a much deeper way. And this blueprint, well, it's the essential foundation for so much more. With the correct order established, the next logical steps would be to use this very same data to calculate the exact distances between the genes, to measure how one crossover event might interfere with another one happening nearby, and ultimately to build a complete quantitative genetic map. So, we'll leave you with this thought. We started with just a jumbled list of numbers, and we ended up with a fundamental piece of the genetic code. This process, this logical deduction, is exactly how we map the very essence of life. So now that we have the key to reading the map, what other secrets do you think are just waiting to be unlocked?